All right, so next up we have Fabian, who's going to talk about guaranteed bounds on posterior distributions.
Okay. Is it on? Yeah, okay. Cool. Yeah, so let me get started with a simple probabilistic puzzle. So suppose you have a fair six-sided die, and you throw it repeatedly until you get a 6. And during your throws, you only observe even numbers. What is the expected number of throws, including the 6, conditioned on this event? Now, this is a fairly famous puzzle, and a lot of people get it wrong the first time they hear it, because they assume it's the same as throwing a three-sided die. Yeah, so maybe a good way to formalize this would be to write it as a probabilistic program, which you can do like this. So we have two variables, number of throws and variable for the die, and as long as the die is not 6, we sample the die, observe that it's even, and increase the number of throws by 1. So even though this is a simple probabilistic program, it poses a couple of challenges. For example, it has variables with infinite support, because the number of throws is unbounded. We have observations and conditioning, and unbounded loops. And it turns out that no existing tool exists, but there's no tool in existence for analyzing this automatically and rigorously. So what techniques are there? We've heard in the previous talk already that there's exact techniques, which give you a precise result. But this is often intractable or requires extensive user annotations, especially if you have loops. You need to provide loop invariants. On the other hand, you have approximate methods, which are always applicable, but have no or few guarantees. So as a middle ground, we're looking in this talk at guaranteed bounds, which are often applicable and give you hard guarantees. So they will tell you, for example, the posterior probability of the variable x being equal to a is between L and U. Guaranteed bounds were, in fact, the theme of my PhD thesis. And we also had a paper at PLDI 2022, where we motivated them with 2 points. First of all, you can view them as safety properties. So you bound the probability of reaching unsafe states. And you can also use them as a ground truth to debug approximate inference methods. In the previous work, this was a very general setting with continuous variables. And if you apply the same thing to discrete programs, it turns out it has quite a bit of overhead. And furthermore, it could only bound probabilities and not moments and tails. And those are 2 points we address in this work. So specifically, we look at discrete probabilistic programs with variables in the natural numbers, and you're allowed to use conditioning and unbounded loops. And we want to automatically find bounds, not only on probabilities, but also on the moments, like the expected value, for example, and on the tail asymptotics, so how quickly the probability mass decreases. And for this, we have 2 approaches. One is called the residual mass semantics, and the other is the geometric bound semantics, which we'll get to later. But first, let me quickly introduce the programming language that we consider. It's a fairly minimal imperative programming language with a fixed number of discrete variables, which, as I said, take values in natural numbers. We have usual program constructs like branching, loops, observations, and we can increment variables by constant, decrement them, and sample from Bernoulli distributions, so do coin flips. And the events we can observe and branch on consist of comparing a variable with a constant and logical connectors. Quick note in the expressiveness. So the deterministic fragment of this language is already Turing complete. And with those coin flips and the other constructs, we can encode many other distributions, such as all finite discrete distributions, geometric distributions, and negative binomial distributions. Some other constructs are hard to encode, though, for example, a Poisson distribution. So what is the semantics of this language? Well, it's typical for such imperative language to have a transformer semantics. So the idea is that your program transforms some initial distribution on the state space of the variables to the distribution you get at the end of the program. So for example, an event would restrict the initial distribution to the states where the event holds. And similarly, a statement would transform the distribution, for example, by incrementing. Like if the statement is incrementing a variable, then the states would be transformed this way, and we would get a result distribution. We usually assume that at the start, all variables are 0. And if you know probabilistic programming well, you've probably noticed that I haven't talked about normalization, but it turns out that it's not, it doesn't cause a lot of problems, so we'll ignore it in this talk. What is tricky, though, is the semantics of loops. The loops are the hard part in this setting. So let me quickly explain their semantics. So if you have such a loop, while E do B, we start with some initial distribution mu, and can describe what the loop does with a fixed point equation. So the distribution mu kind of flows in, and then a part of the distribution exits the loop immediately if the loop condition is not satisfied. But some part of it enters the loop, is transformed by the loop body B, and then fed back into the loop again, which gives you this fixed point equation for the semantics of the loop. So first, let's look at how we can get lower bounds for this. This is a well-known technique. We can just unroll the loop a few times, and we will get a lower bound as follows. So we take the fixed point equation, apply it again on the right-hand side, and at some point, we just say the loop will produce a measure that's at least 0, so we get a lower bound like this. So here we did 2 unrollings, but you could do more. This has a lot of advantages. It's easy to compute. In our setting, we only need finite discrete distributions during the computation, and it converges to the true distribution as you increase the unrolling. Upper bounds are harder. So we come up with the following idea. As the probability distribution flows through the program, we can look at the total probability mass. So initially, this will be 1. And then in each loop iteration, some of the mass will flow out of the loop. So we can bound the residual mass that's still inside the cycle if we just take the difference between the initial probability mass that has flown in and the lower bound that we computed with the unrolling. And this way, we can bound the probability of an event S at the end of a program, of the loop, by just taking the lower bound and adding the residual mass, because there's no more mass left, so this will be an upper bound. So this is a fairly simple idea, but it works quite well. So if we apply this to the example from the start, here with 40 unrollings, we are orders of magnitude faster than previous methods. And as you can see, so on the x-axis, we have the number of throws, and on the y-axis, the probability mass on a log scale. So you can see up to the unrolling limit, it's very good, and then we kind of have this flat bound because, yeah, this is the residual mass. Because of this flat bound, we can't get non-trivial bounds on the expected value, because this will just be infinite, because there's infinite support. So we want to find more informative bounds. And for this, let's look at this flow diagram again. And the idea in the previous, for the residual mass, was to look at something that decreases, which will be the residual mass. And now we'll think about what happens if the distribution itself decreases in each iteration uniformly. And even better, if it decreases by a constant factor less than 1. Well, it turns out then we can do something quite nice, which is if we take this fixed point equation again, we can pull out this factor c and move the second summand to the other side, divide by 1 minus c, and then we, ta-da, get a bound on the distribution of the loop. Of course, this condition of this uniform decrease by a factor of c will not be satisfied very often. But it turns out that in many cases, we can find a kind of slightly larger distribution, nu, than mu, which satisfies this condition. So this is kind of analogous to strengthening the inductive hypothesis in a mathematical proof. So just to define this properly, we call this concept a contraction invariant, because the distribution contracts by a factor of c. So if we have an initial distribution mu, then a contraction invariant is another distribution nu that bounds mu, and that decreases uniformly by this factor c. And by the same argument as in the previous slide, we can then bound the distribution of the loop on mu using this contraction invariant. Another question is, how do we find such a contraction invariant? The space of possible distribution is huge, so we have to somehow restrict it. And we have to restrict it to a class of distributions that have non-trivial tails and tails that we can reason about easily. So our first idea was to look at geometric distributions, because there the tails decay exponentially, and that's very simple behavior. And in fact, you can compute the moments in tails easily, but the problem is that geometric distributions are not closed under many operations that you would like. For example, if I increase a variable by 1, it will not be geometrically distributed anymore. So we generalized geometric distributions to something that we call eventually geometric distributions. So we allow them to differ for first few values, for small values, which we call an initial block. So we write this as follows. So EGD, some initial block, and the decay rate means that the initial probabilities will be those indicated in the initial block. And from then onwards, they decay exponentially with rate alpha. We can do this in higher dimensions as well. For example, here we have a 2x2 block. And in one dimension, the probability mass decreases with the rate alpha, and the other dimension with the rate of beta. So this class of distributions has some nice properties. It's still easy to compute probabilities, moments, and tails because they rely on geometric distributions. But they're closed under many more operations. For example, increment and decrement. All right. So we have to build a semantics that operates on these EGDs and yields upper bounds. And contrary to before, this cannot really be a transformer semantics, cannot be a function, because there may be many upper bounds that are valid. So instead, we defined a relational semantics, PGO, which relates pairs of distributions. So the way you can think about this is the distribution EGD P alpha is related to EGD Q beta. So this is designed to ensure that when I run the program P on this initial distribution, the result will be bounded by the right-hand side. And it turns out we can define this semantics in such a way that this relation reduces to polynomial inequality constraints on the parameters of the EGDs. And this is nice because solving such inequalities is decidable. So for a given initial distribution, you can decide whether there exists an upper bound. So we have a couple more theoretical results in our paper, which I'll just quickly mention. First of all, of course, you want this to be sound. It turns out it is, both semantics. We also have a convergence result. So both bounds converge in total variation distance to the true distribution as you unroll the loops further and further. Terms and conditions apply. Details are in the paper. And we also investigated when such bounds exist, because it might just be the case that this system of polynomial inequalities has no solution. And we found some sufficient and some necessary conditions for the existence. So let's see what this method can do for our introductory example. So again, we see the probability masses plotted, in green the exact probabilities, and then I'm showing two geometric upper bounds. This comes back to the talk, as I mentioned before, to the point I mentioned before, that there can be more than one upper bound. And in fact, these two upper bounds have different trade-offs. So the one in blue is optimized for the total probability mass to be as low as possible. And the other one is optimized for the tail asymptotics to be as good as possible, which is why the black line is much steeper than the blue line. But on the other hand, it's worse for small values. Right. So the original question was about the expected value of the number of throws. And so the exact value is 1.5, and our method gives a very tight bound on this in less than a second. And we can also bound the tails. The true tails decay with a rate of 1/3, and we can find 0.34, so also quite close. We investigated the usefulness of the method more systematically. So we collected 43 benchmarks from the literature on probabilistic program analysis and added some of our own. And for 37 of those, so 85%, our geometric bound semantics can find an upper bound. And this includes many examples that could not be automatically analyzed before. In terms of performance, the running time was usually a few seconds or less. For complicated examples, it went up to 5 minutes. The quality of the bounds is difficult to summarize, but I would say it's usually quite tight. But it gets worse for distributions with heavier tails. We also compared with some previous tools. And the summary is that our tool supports more benchmarks and is often faster. So in summary, I've presented to you two techniques to find guaranteed bounds for the posterior distribution of discrete probabilistic programs, residual mass semantics and geometric bound semantics, and introduced some novel concepts such as contraction invariants and eventually geometric distributions, which I hope will be useful maybe in other probabilistic program analysis techniques in the future. Thank you for listening, and I look forward to your questions.
Thank you so much, Fabian. Any questions?
Hi. So you mentioned that you it works. So that you identified some of the necessary and sufficient existence criteria. How many? Can you describe how many of these criteria are at least somewhat automatically checkable? So if I have a probabilistic program, can I just look at it and relatively easily see, oh yes, it satisfies or it doesn't?
Easy syntactic criterion. Because for example, if you look at a random walk, biased random walk, then if it's biased towards going back to the origin, then such a bound exists. But if the probability of going to the origin is 1/2, then the bound doesn't exist anymore. So it kind of depends on the exact values that occur in the program. So there's no easy, purely syntactic criterion. But we have a theorem that involves an additional condition of some martingale to exist. And then we could show that under certain other assumptions, something like this exists. So yeah, a bit more than syntactic.
Thanks.
Hi, thanks for the great talk. I have a question about the last curve that you showed. You said you can have multiple upper bounds. And as a user, how do you choose which one to?
What objective you want to optimize for. So you can say, for example, I want to minimize the total mass of the bound, or I want to minimize the tail behavior. Like I want the tail to decay as quickly as possible, or I want to minimize the expected value of the bound. So the user can specify the optimization objective.
Right, but you have a finite set of choices that you program somehow in your system. And we need to choose about.
Yeah, so currently, yeah, we implemented a finite set of choices, but in principle, you could support anything that polynomially depends on the parameters of the EGDs again.
Cool. Thanks.
Thanks for the talk. You mentioned higher moments. Can you say a bit more the challenges involved in computing them? Because they're not linear, right? So I assume some of the tricks that you can use for probabilities do not quite work there.
So you said they're not linear? What do you say? I didn't quite hear.
So higher moments are not linear. So some of the nice tricks that you have for computing expected values and probabilities do not quite work there.
Right. So for geometric distribution, there's like closed form formulas for how to compute the higher moments. And we were able to adapt those to EGDs as well. So in the end, it turns out it's just some rational function in the parameters of the EGD. So it's possible to compute it. Yeah. And everything stays polynomial. So.
Thank you. Your semantics seems to consider only terminating programs. Can you extend to then some that do not terminate? For example, you would like to know my program never terminates, but the probability that x is greater than 10 is very small. This has a lot of application in the avionics industry where they must anticipate the probabilities of failures.
Right. So the second semantics, the geometric bound semantics, only works if the program is almost surely terminating. In fact, it has to be positively almost surely terminating. The other semantics you could apply, but you wouldn't get convergence of the bounds. So for the bounds to converge, you need your program to be almost surely terminating.
It should be possible.
Yes, your bounds won't be super tight, but it should be possible, yeah.